Hi, everyone. My name is Ali. I am a chemistry Fresno State Learning Center tutor. I'm here to show you today the Holy Trinity of Energy. As you can see on my screen, there is this triangle with energy right in the middle, E for energy. And as you can see, energy has three lines connected to it. It has a line connected to hc over lambda. If you remember from your chemistry classes, H means Planck's constant. We know that C stands for speed of light. And we know that wavelength, or lambda, sorry, stands for wavelength. Now, what are the units of these? That's a good question. Planck's constant, well, it's pretty typical. It's a specific constant with a specific units. I'm going to scroll down. I have some questions here that I will show you later. But as you can see, it's joules times seconds. So that is our unit. Joules times seconds. Speed of light is going to be meters per second, or meters divided by seconds. And wavelength is going to be in nanometers. But sometimes they may ask you to express it in meters, so you need to pay attention to that as well. Okay, let's go down. So energy, we know that energy is equal to hc over lambda. The line connected to it means that it's connected. Okay, let's go look at another edge of that triangle. If we come over down to the left side of this edge here, we get that E is equal to H, and this little, it looks like a V, but it's not quite a V. It's actually called a nu. It's a Greek letter. Remember from earlier, we said that H is equal to Planck's constant, and that V actually, or that we call it nu, is frequency. So frequency has two units. There's hertz, or hertz is also equal to this, 1 over seconds. You may see it as s to the power of -1. That's the same thing as 1 over seconds. I highly encourage you guys to express it as s to the 1 over s, because that is easier to work with when you're canceling out units. So E is equal to Planck's constant times frequency. Cool. All right, let's go to the other edge. E is equal to plus or minus RHC 1 over NF squared minus 1 over NI squared. Okay, what does RHC mean? That is a constant, Rydberg's constant. So something that should be given to you on your exams and other things, on your formula sheets and other things. Yeah, that is equal to 2.179 times 10 to the power -18. And just to refresh me on units, our units are going to be, well, we don't have to worry about units actually for this one because it's not that important. Rydberg's constant does not have units. Okay, our NF stands for energy level final. Energy level final. There's no units attached to that. And NI, can you guess what that is? Energy level initial. All right. Now you might be asking, what does that plus and minus mean? Well, plus tells you that you're absorbing. You're absorbing. That means like you're gaining. That means that you're going from a lower energy level initially to a higher energy level. So for example, you're going from 1 to 3. That is absorbing. That is an example of absorbing. Your N changes from N equals 1 to N equals 3. You're going from a lower energy level down to or that's going to be very important to know. This is the Holy Trinity. Sorry about that. My Wi-Fi just cut, but we'll just continue from where we left off. So I was mentioning this triangle here is the Holy Trinity of Energy. One thing you'll notice is that E is equal to 8c over lambda. And we also know that E is also equal to H frequency. So what we can actually do is set that equal to 8c over lambda, H times frequency. And we also know that is equal to plus or minus RHC 1 over ns squared minus 1 over ni squared. So as you can see, everything is connected within this Holy Trinity. This H frequency is equal to RHC equation. We have HC over lambda is equal to H frequency. And so this is going to be very important because everything is connected here through energy. That's why we call it the Holy Trinity of Energy. That's the main three formulas that you need to know here. Excellent. Awesome. I hope this answers a lot of your questions on this. Now let's do some problems. Let's do some example problems. So let's look at this one. An electron transitions from an excited state to a lower energy state in a hydrogen atom. If the wavelength of the emitted photon is 486.1 nanometers, calculate the energy change in joules during this transition period using the equation E equals hc over lambda. Great. So they give you all this stuff. They give you all the background. Now, a lot of these questions you may see on your exam or homework, they won't tell you which equation to use. So you need to be very careful. You need to be very, very careful. Yeah, so you need to be very careful and need to listen. Need to look out for a specific formula. Pick out the ones. So I always do is write out your given. So you're given in this problem, we're given we know that the wavelength, so we know wavelength is equal to 486.1 nanometers. Okay. And we need to find energy. All right. And we know what H is. H tells you it's 6.626 times 10 to the negative 34. H will never change. Joules times seconds. And we know that C is equal to 3.00 times 10 to the power 8 meters per second. All right. Now, there's one issue here. If you look at this closely, you need to try to find joules. It tells you right here, in joules. So that's the last unit you're going to end up with. Now, how can you end up with joules here? So let's look at it. If we try to match up the units, we know that there's seconds and seconds right there. Okay. We know that there's joules, which is what we need, so we don't want to match that up. And we need meters and meters, but there isn't meters. There's only meters and nanometers. So what that tells us is we need to convert nanometers into meters. So before we go ahead and do this stuff, so let's do that. So 486.1 nanometers. Okay, we start off with that because that is our non-ratio number. And what goes on the bottom? Nanometers. Right. And what goes on the top is meters. All right. Now, if you remember from your conversion sheet, look on the back of your periodic table. Hopefully, there should be a little conversion table there. We know that 1 nanometer is 10 to the negative 9 meters. Yes, 10 to the negative 9 nanometers. So what that tells us is we go ahead and cancel. And so we get 486.1 meters. Or sorry, times 10 to the negative 9th meters. All right. Now we just plug that into our equation. E equals, we know that's lambda, or we know, sorry, that H is 6.626 times 10 to the negative 34. I always recommend you guys put your units in your equation. Units are incredibly important in chemistry. Don't forget that. Times C, which is your 3.00 times 10 to the power 8 meters per second. And then finally, you put it over lambda. And we know that lambda, or new lambda, is 486.1 times 10 to the negative 9 meters. Okay, now look at this. Meters and meters cancel, seconds and seconds cancel. Our end unit will be something in joules. So I'm not going to calculate it for you guys, but I'm hopefully you can put it into the calculator properly. If not, you can always come visit us down in the Learning Center. We can help you understand how to put things in a calculator. But try calculating that on your own and see if you get some answer that works out. Okay, great. So we'll move to the next question. Experiment is conducted to study the photoelectric effect. A beam of light with a frequency of 5.00 times 10 to the 14 hertz is directed onto a metal surface. Okay, when you see that, hertz, what does that remind you of? Frequency, right? So let's write out our givens. I know I should have finished the problem before writing this out, but let's just go ahead and write it on the fly. 5.00 times 10 to the power 14th, and that's going to be in hertz. We also know hertz is 1 over second, so I'm going to put that in parentheses. Okay, the next part. Calculate the energy in joules, so that's what we're looking for. We're looking for energy in joules of the photon in this beam using the equation E equals H times frequency. Okay, pretty simple so far. Okay, yeah, so we know we're using E equals H frequency. These problems are pretty simple in terms that they tell you which equation to use, but that won't happen to you on exams and homework. So try to deduce that using the given. All right, so E equals H times frequency. We know that H is 6.626 times 10 to the negative 34 joules times seconds. We can write that in our given. Okay, does everything look right? Yes, it does. We have seconds and we have 1 over seconds there, so we know that will cancel, and we're looking for joules. That's perfect. Awesome. All right, so this is pretty easy. So we just plug it into the equation. 6.626 times 10 to the negative 34 joules times seconds. And then we put our frequency in there, 5.00 times 10 to the power 14th, 1 over seconds. Seconds and 1 over seconds cancel, and we are left with just joules. Excellent. Also, awesome. Go ahead and calculate that out and see if you get something that makes sense. Okay, let's go to the next one. So, as you can see the pattern, we used 8c over lambda, we used H times frequency, and now we have an RHC equation right here. Consider a hydrogen atom in its ground state. Using the Rydberg equation, calculate the wavelength of the spectral line corresponding to the transition of an electron from the n equals 2 energy level to the n equals 1 energy level. Okay, so we know that we have the n equals 2 and n equals 1. So n equals 2, it says transition of an electron from n equals 2. So that's where it's starting. So that's what's going to be our Ni. It's 2. And we know that we're ending up on 1. So NF equals 1. Okay, another thing we need to start thinking about, are we emitting or absorbing? Well, we're starting at the higher energy level and we're going down. So that means we're emitting. So our equation should be E equals negative RHC 1 over NF squared minus 1 over NI squared. You see how I dropped that positive? Now I'm just talking about that negative. All right. So we know what our Rydberg is. We know what our RHC is. That's going to be our 2.179 times 10 to the power negative 18. You don't need to worry about units there. And we should have everything to go ahead and do the calculate this out. So E is equal to negative 2.179 times 10 to the power negative 18 times 1 over, NF was 1, so 1 squared minus 1 over NI squared, which is 2 squared. Cool, so let's simplify that. So we get E equals negative 2.179 times 10 to the power negative 18. And that would just be 1 over 1, which we know is 1. So we'll just put that as 1. Minus 1 over 2 squared, which is 4. Cool. And we can also turn that 1 into 4 over 4 now, since we know that that is also equal to 1. So we know that E is equal to negative 2.179 times 10 to the power negative 18 times 3 over 4. Or if you want to convert it to decimal, you can put it as 0.75 and put that into your calculator. And doing all that should give us our energy level. So go ahead and try calculating that out and see what we get. All right, cool. Let's go to our last one. So this might be a little bit new. This is called the de Broglie wavelength equation. So I'll write that down up here. The de Broglie wavelength. All right, this is something is not included in the Holy Trinity, unfortunately. But it has a very simple formula, I should say. All right, so let's read the question. It says, calculate the wavelength produced by a 25-gram frisbee that travels 15 meters per second given Planck's constant. Okay, awesome. So let's write out our givens. We're given 25 grams. So we know that 25 grams is also equal to mass. 25 grams. By the way, I should give you your de Broglie's wavelength equation. Maybe that should make it a little bit easier. That is wavelength is equal to h over mv. Remember, we know that h is Planck's constant. The only new things that we need to pay attention is m, which is mass. And this is going to be in kilograms. So that's your unit, kilograms. And then v is actually not your frequency. This is actually true v, not new. True v. That stands for velocity. If you remember from the physics classes, if you've taken them, velocity units are meters per second. All right, cool. So going back to our givens, we're given 25 grams in frisbee. So we know immediately that we need to convert that to kilograms, but we'll do that in a second. Okay, we also have our velocity, which is 15 meters per second. And of course, we have our Planck's constant, 6.626 times 10 to the negative 34 joules times seconds. Awesome. All right, so we talked about converting that mass. So let's go ahead and do that. It's 25 grams. And we know that there's 1,000 grams in 1 kilogram. Review your conversion table if you're not sure about that. That cancels. And that should give us our 0.025 kilograms. All right, cool. So we got our kilograms. Now we just plug into that de Broglie's wavelength equation. To remind you, it's wavelength equals h over mass times velocity. All right, so now wavelength is equal to our 6.626 times 10 to the negative 34 joules times seconds. Divide that by mass, which is 0.025 kilograms, times your velocity. Your velocity is 15 meters per second. Awesome. All right, and then if you take a look, meters, seconds cancel. Now this is a little bit complicated. Joules over kilograms times divided by meters. It's a little bit complicated in terms of you don't really need to pay attention to units here. I know we're looking for wavelength in nanometers, and that's what it's going to give it to us in. But wavelength in meters. So don't pay attention to the joules and kilograms. Pretend they cancel out. There's a lot more calculus-based stuff going on here, and I don't want to go through that for an introductory chemistry class. But just only pay attention to that unit. So or just pay attention to that meters. That meters is important. So our answer is going to be in meters. And most of the time they'll ask us to calculate it in nanometers, so you'll have to do a conversion. But I'm sure you guys can do that. All right. Well, check your answer, calculate this out, see if it makes sense with the problem. But other than that, yeah, that is our main equations here. So remember this Holy Trinity here. E equals hc over lambda, or wavelength, is equal to h times frequency, which is also equal to r plus or minus rhc 1 over nf squared minus 1 over ni squared. All right. So if you ever need help with this, come down to the Learning Center, and we can help you out in learning this Holy Trinity. But this is essentially the main concept of pretty much your math part of the quantum mechanics. All right. Well, I hope you guys enjoyed this recording and learned a lot. Again, stop by the Learning Center. We're here to help you out. But for now, peace.